So let me come back. So yesterday we discussed, we started with C1 solution. We started with C1 solutions. C1 solutions to the one space dimension. When U is C1, this becomes, if everything is smooth, we can rewrite the PDE as in this way, and this is a quasi-linear PDE. U C1 quasi-linear PDE, and then we have the system of characteristics that we have discussed yesterday. But we have seen that the interesting phenomenon is that two projected characteristics, can intersect. And this leads to the failure of, say, can intersect corresponding at, say, at T sing x, and then we cannot use anymore. We cannot use anymore the method of characteristic system to have a solution for T larger than T sing. To construct a solution PDE for T larger. This is the problem that we have to face. So this leads to some notion of weak solution global in time, defined for all T positive, is required for all T, say, or for almost all T, or almost all T, say, is required. Do you agree with this philosophy? This is a typical phenomenon, typical way of reasoning for several PDEs. We produce a PDE which, starting from a smooth U0 smooth, starting from initial condition, the solution singularized at some time, T sing. So we cannot define a C1 solution after T sing, at least using this method of characteristics, because U is constant along characteristic, and we don't know how to go back from T sing to T equals 0, in which of the two or infinitely many possible ways. And so some notion of weak solution defined for any T is required. So now I would like to do some, say, exercise. The first exercise. Okay, but we will suppose always from now on that the flux is C2. Okay, from now on flux is C2 and is strictly convex. just to be, not to have too many difficulties. Okay. So exercise. Suppose that U0 is C1 of sigma. Sigma is equal to R. Can be identified with R. And U0 prime is less than or equal than some constant C1. Okay? And suppose that F along U0 is, so this is for any y, for any z. For any z. And suppose that f of u0 of z is less than or equal to some constant C2. Then T sing is larger or equal, say is larger, to be sure, 1 over C1, C2. So for some time we don't worry about, because so C1 solution exists in a strip, but up to TC. Okay, so yesterday how do we do this exercise? Yesterday we introduced a function, I call it G, I think, capital G. Capital G. The definition was it was how to invert the characteristic. No? So it was G of T, Z, and X, and the characteristic line is Z plus T. T of prime U0 Z minus, do you remember? It was this, no? And the problem was to solve this equals 0. So G equals 0. Meaning that we want to extract Z given X and given T. T is a parameter. Given X, we want to find T, Z. And if we differentiate this with respect to Z, so what happens to this is 1 plus T, F is C2, no? U0 is C1. So this is surely larger or equal than what? 1. T is positive, see? T is always positive, we go into future, okay? So F0 in absolute, this is positive and is less than or equal than C2 by assumption. We don't know about the sign of U0, but its absolute value is less than or equal than C1. So at most, this is larger or equal than T, C1, C2, right? Which is positive as soon as T is less than 1 over C1, C2. So let us put larger or equal. So this means that as soon as T is smaller than 1 over C1, C2, we can invert this G equals 0, so by the implicit function theorem, we can deduce z given x. And therefore there are no problems in this case. So this thing we can estimate from below by this constant. This is one example. Another exercise to do. Exercise similar in spirit. So consider Burger's equation. So n is equal to 1 in all the lecture. N is equal to 1. So in one space dimension. So suppose we are in Burger's case, strictly convex and smooth, and suppose that we take u0 of z is equal to 1 divided by 1 plus z squared. Okay, we want to, if you remember the notation of yesterday, I wrote that the map capital phi was invertible, say, into phi of 0 delta times r. For some delta positive, we know that this map is invertible on its image, but this delta is not necessarily equal to plus infinity. So let us write estimate delta. It's similar in spirit as here, okay? Estimate delta. So for how much time we are sure that the method of characteristics is okay. Notice that this is an interesting initial condition, because the initial condition is sort of function like this, and we know that this PDE makes a big difference between regions where I am increasing and regions where I am decreasing, right? Do you remember? In particular, region where smooth region here I am increasing, what I expect is to see something, because the velocity is, if I am higher, the horizontal velocity is higher toward the right. Huh? So what do we expect? We expect some, as time goes on, maybe say something like this, and then as time goes on. And so at some time we can expect a situation like this. So. And this is due to the fact that no problems arise here, but big problems arise in the regions where u is decreasing. Okay? Do you remember the discussion, yesterday's discussion on the horizontal velocity? That was just heuristic. Eh? Okay. Okay. So, what is this thing? Here is the infimum of all positive times, such that you remember the map phi was rank 2 for short times. But we cannot say that it is always rank 2. It maybe drops rank at some time. So we take this. So you compute no, you can write this. This is z. Let me write it, the determinant of grad phi Tz is equal to 0. Okay. But what is the determinant? The determinant of grad phi of Tz, we computed yesterday, let me copy. Determinant equal to 0 means, if you remember the computation of yesterday, means, so the determinant of grad phi, it is this. If and only if t is equal to minus 1 divided by this. So if you look yesterday notes, so U0 prime is so this implies that determinant equal to 0, 1 over, okay. So U0 prime of Z is, U0 is here, so we have minus 2Z, right, 1, 1, plus 1, that's 2 squared. Okay. Okay. So this is the freedom of T positive, this Z and sigma, such that I write it 1 minus 2zt. This is one way to write it. Two zt here divided by 1. Okay. Or this is equal to T is equal to 1 plus Z squared divided by 2Z. Okay, so what is this function? It's a function that, so we have to minimize this function in T, in favor of this T, so we have to minimize this in Z. And so we found that if we differentiate with respect to Z, then we put it this equal to 0, so 1 plus Z squared divided by 2Z equals 0 gives Z squared equal, sorry, Z squared, this is a computation, 1 over 3. Okay. And you put it here, and you find that this thing is, so you just write Z squared, Z1 over square root of 3, you put it here, you find this thing, and this thing turns out to be this, computation 8 over 3 square root of 3. Okay, so before that time that we have explicitly computed in another way, so where this capital phi is not anymore a diffeomorphism, before that we can use, so before this thing, so for T less than this thing, you can use the method of characteristics. Okay. So the method of characteristics gives us what? There are various ways to write it. For one way is to write this equal U0 of Z. No? So we cannot, this is one way. You remember, U is constant along characteristics. So this is what we called, maybe this was what we called y of t, no, yes, y of tz. Or in other coordinates, U of tx is equal to U0 of Z of Tx. Huh? So it's a little bit implicit, unfortunately. We cannot, so this is one way, or if you want to use coordinate Tx, we have this, 1 plus Z squared, yes. So with our notation, this was y of t y of t, z of t, x. And so this is equal to 1 divided 1 plus z squared dx. Okay, there are various ways, but they are always implicit, unfortunately, because we cannot explicitly find given x capital Z of the inverse. We know it is invertible. But we are not able to invert it explicitly, so we have to keep it implicit, the expression. Okay. An interesting way to write it here, which is the relation. So the relation is that x is equal to this. So x minus z of tx divided by t is equal to f prime of u0 of z of tx. Okay. So if you want, u at time t point x is u0 at this capital Z of tx, which is the relation between tx and capital Z. It is given here, but unfortunately you cannot write it explicitly. In the linear case, we found explicitly the inverse, and it was x minus ta. You remember? Now, unfortunately, it remains implicit. And okay, so this is so remember this expression relating the given by the system of characteristic. By the system of projected characteristics. Oh, in Burgers, this becomes, for Burgers, f prime is the identity, so we have this interesting expression, because f prime of y is y, so f prime of this is this itself, so it's equal to okay. This is another exercise. Let me see once more, just to take confidence with this kind of implicit formulation. So you see, there are two novelties here. First of all, the characteristics intersect, and also before they intersect, we cannot really invert explicitly the map capital X given by the system of characteristics, and we have to keep its inverse, and we have to write the relation between the two. Okay. Another exercise. Consider once more Burgers. And u0 of z sinus of z. Again, this is not increasing, so there are regions where it is decreasing, so we expect that this thing is finite. What can we say? So T sing is larger or equal than 1. Why it is so? Because u0 prime is less than or equal than 1. Okay? And f second is 1. So we can take C1, C2 equal 1. And therefore, from this exercise, indeed, C1 equal 1, C2 equal 1, and we can apply, and we can directly apply this exercise. Okay, let's see what happens. Let's see what happens if I have a picture. I don't know if I was able to draw a picture so that I can. Ah, yes, I have a picture. So let's see what happens at the singularity time. So what is blowing up exactly? So compute ux. Okay. So what do we know? How we compute ux? Okay, what do we know? U of tx, we know that is equal to u0 of z of tx. Okay, this we know. Z is implicit. But u0 is given. So u0 is sine. So this is sine of z of tx. For t less than t sing, less than 1, say 1. We don't know. We still don't know that t sing is exactly 1. But so I claim it is 1 at the posteriori. So in any case, for t less than 1, we can compute. So this is cosine of z, zx, and ut equal cosine of z, zt. Okay, from that. Everything is, so for t less than 1, everything is C1. We can do all derivatives that we want. Okay. Now, how we have to compute zx and zt. Okay. Still, we have, remember, our equality. X is equal to capital Z of tx plus t f prime is the identity, sine of z of tx. So from this we can differentiate with respect to t, this identity, and we can differentiate with respect to x, this identity. So what do we get? So if we differentiate with respect to x, we get 1 is equal to zx plus t cos zx. Instead, if we differentiate with respect to time, we get 0 equals zt plus sine z plus t cos zt. So from the first one, we can find zx, which is equal 1 divided by 1 plus t cos. So this is equal cos z plus t cos z. And from the other one, we can deduce that this is equal to minus sin z. So it is equal to minus sinus of z cosine of z divided by 1 plus 1 plus t cos z, right? Let me check. I don't know if I wrote it. What do we see? Okay. So st goes, so as z converges to pi, and st converges to 1 minus, we get that ux blows up. Ux. No? From this, because you see that this denominator, this goes to 1 minus. If this goes to pi, this blows up. So, and it happens exactly what we expect, that there is ux, meaning that if it blows up, it means, so morally, a vertical part in the graph. No? When the derivative is plus infinity, you're verticals. So, and I try to do a picture. Now let me try to do a picture for you. I don't know if it is useful, I hope. Let's draw the plane Tx, T vertical axis as usual. I draw the characteristic lines here. This is 1. This is pi over 4. This is pi over 2. Then we have 3, 4 pi. Then I have pi. Then I have pi, and somewhere I have 2 pi here. See? Let me draw, I try to draw the characteristic lines. You see? At time 1, in corresponding to the coordinate x pi, we have a point where, in time space, where the characteristics meet together. And now let me try to do the graph of the solution. U. So the initial condition was sinus, so something like this. Okay, this is in the plane t equals 0. This is the initial condition, u0. Okay, graph of u0. Let me see if I'm able to draw something. can you see it? This is pi, yeah? This is pi. So when you differentiate with respect to x here, what do you see? There is time 1 somewhere here. And after this time, if I look at the union of the characteristic lines, characteristic means I am constant height, no? What I produce a fold, right? But this is not anymore a graph. No? So I have to stop here somewhere, and this fold cannot be considered in our language a solution of our problem. So after this time, this fold I cut it, put a vertical wall, and then there is a discontinuity there. No? Even if this manifold, which is union of lines, sort of ruled surface, is perfectly smooth, but we cannot accept it because it's not a graph. And we are, from the beginning, we are looking for a map. So we cannot have a multivariate map. We don't accept this. Okay. So now, this I hope that I have convinced you. We have done 3 examples of two at least, 2 examples of singularity formation, meaning that the gradients blows up, which means that U becomes discontinuous, gradient in space, which means essentially that U morally becomes discontinuous, and this is due to the part of the initial datum, even if it is very smooth, the part where the initial datum is decreasing. But it is clear that this PDE distinguish regions where U, because ut plus ux, it's clear that here the PDEs must be sensitive of the sign of U, of the behavior of U. No. Now, so this leads us to the notion of weak solution. Now, the problem of weak solution is very huge. In this course, we do only distributional solutions, but we can invent several notions of different weak solutions, differently defined. Maybe in this case they coincide, I don't know, but let's insist on the distributional one, which seems to be, at least for this PDE, which are divergence form, seems to be very convenient. So now, after our experience in the linear case, I think that you can accept the definition of distributional solution. So let me give it for you. So definition. So suppose that U0 is in L1 log, actually. So even discontinuous, whatever, even smooth, all the initial conditions that with sinus 1 over 1 plus z squared, they are all in L1 log. Okay? But L1 log allows more, in particular discontinuous initial conditions, which are very interesting. In any case, so let U0 in L1 log and suppose that F, okay, let's U0 in L1 log. We say that U is a distributional, or weak is a distributional solution of ut plus f of u x equals 0, u of 0 equals 0, you can imagine, no? If the observation is simply that this is the time-space divergence. So we can put the derivatives on the test functions. Okay? So if what? So this is, say, in 0 plus infinity times r on sigma. If u is in L1 lock, f of u also, and for any phi, say C1, sufficient. And now it's important that zero plus infinity times r, we have integral u phi t plus f of u phi x dx dt plus integral phi of 0x u0 x dx equal to 0. After our experience in the linear case, we accept this is based on the fact that simply we can integrate by parts, put the derivative here, etc., etc. We have already discussed this. Okay? Now, of course, we have something nicely defined, but we don't know about anything about this. So, existence, uniqueness, etc. So, a new fact I anticipate here, in general, not always, but in general, distributional solutions are not unique. And again, a new phenomenon. Solution may be not unique. So, this opens an interesting question, which means that if we want to go on after TCing and give a reasonable notion of solution, we would like to detect among the infinitely many distributional solutions one physical solution, just only one. So this is not enough, and we will need some more restriction. So one needs to add to this infinitely many equations one more restriction. We will see an example of non-uniqueness, okay, of distributional solutions. So this is a clever way, but one needs to work more. Otherwise, one doesn't know which is, if there is a preferred solution or not. Okay? Okay.
A question. If we had the increasing, we had to test function to be also increasing, let's say, or not decreasing. Even this doesn't.
No, you don't need to do any kind of restriction on phi. Phi must be, the restriction it must be compactly supported. This is the only restriction. But it is not necessarily 0 on sigma. Compactly supported, but not necessarily 0 on sigma. Otherwise, you don't detect the initial condition. This is the only restriction that you need to do. Okay? So similarly, you can define this in an open set. Okay, you can imagine similar definition. In omega open. Just localize test functions there. Okay, so remarks. I leave you to think of these remarks, which are interesting. Okay, first of all, so which is suppose, okay, remark. So suppose that everything is smooth. If U0, say, is C1, and suppose that U is C1 also, and suppose that U is a classical solution, in the sense C1 solution, then U is a distributional solution. It's easy to see this, no? So, because you can integrate by parts. If U is C1, you can put phi here, the derivative here, the derivative here, and then this must be 0, because this is a classical solution. And then you realize that after integrating by parts, U must be also equal to U0. So it's not difficult to try to do this. So this means that strong solutions are weak solutions. So we have a family of solutions, strong solutions. We have a family of weak solutions. Strong solution must be, as soon as they are strong, classical, they must be weak solutions. What about the converse? So suppose U is a distributional solution in an open, and suppose that U is C1 in an open set. So if you know a priori that your distributional solution is smooth in an open set, then there is a strong solution. Then U is a C1 solution in omega for the same reason, essentially. If omega, if say U is C1, 0 plus infinity times R, then if also, then 0, 0. U of 0 equal U0. If also, suppose U0 small also. Okay, now we have a necessary condition which is interesting, which is called, so now on the lemma, okay, or maybe proposition. This is called the Rankine-Hugoniot condition. It's a necessary condition under some smoothness assumption. Hugoniot condition. So I will do some sort of assumption, but I need some smoothness, unfortunately, to do. So let me try to write it. Let U be a distributional solution. solution such that, now let me try to write it in some way, such that we have, so this is time space, and then we have some curve here, okay, some curve here. Let me call this gamma. This is such that this curve is the jump of u. Oh no, it's just gamma. Okay, such that u is C1, where, say, in the region, so such in the region, such. So maybe it's better first to define such that there exists gamma, which is the image of a map gamma with T saying some AB. Okay. So this is just the image of a curve. This is gamma. So gamma is where small gamma is C1. So I take simply a piece of curve, C1, but this curve is graph with respect to this this axis here. So it cannot do this. Cannot do this. Gamma is this. C1. There exists gamma such that u is C1. Say here I have. Where is C1? Is C1 for T x on this side? I don't know if I have to give a name. So let me call this omega minus, and let me call this omega plus. So it's C1 in the open set omega minus, and U is C1 in the open set omega plus. So omega minus consists of all times larger or equal than, say, Tx, such that T is in AB, and X is what? X is less than gamma T, and omega plus instead has Tx. And suppose that U is C1 on both sides, but here it jumps essentially. So we are taking a distribution solution which is discontinuous, no? But reasonably discontinuous. What does it mean? It means that it is smooth out on the left of this curve, smooth on the right, maybe jumping on this curve, but this curve is smooth. And the jumps also, so you such that there exists u minus of t equal limit as x goes to gamma t x say omega minus of u tx, and there exists u plus of t equal limit x to gamma t x, sorry, tx in omega minus tx in omega plus. So there exists the limit from here and from here for any t. So, and we suppose that this trace is, so I'm essentially I'm looking at the value of u from the left on this curve, u minus, and the values of u from the right. U is discontinuous possibly, but it leaves two traces which are supposed to be continuous. So u plus and u minus are supposed to be continuous. Suppose u plus minus continuous. Okay? Something like this. So, what I would call this distributional solution, how we could call this? Piecewise smooth. Okay? It's a way to say it is piecewise smooth, but it's very difficult to make rigorous the word piecewise smooth. Okay? So it's piecewise in this sense. Okay. After this, so you distributional solution piecewise smooth. Then, and then Ranchino-Gognot. I try to write it here. So gamma prime of t, u plus of t minus u minus of t, this is equal to f of u plus of t minus f of u minus for any t. This is called the Ranchino-Gognot necessary condition. So let us call this for simplicity piecewise smooth. But this is not undefined. Piecewise smooth in this sense is not something with, okay, what is smooth here, smooth there, what does it mean? It's piecewise smooth in this sense. Fine. So if it is piecewise smooth, then the slope essentially of this curve is forced by the values of u plus and u minus. We can write this in another way using the normal to the jump. Say the normal going from u minus to u plus, but then, okay, the normal, one of the two, nu u times the vector u plus minus u minus f of u plus minus f of u minus, this scalar product must be 0. It is an equivalent to A on gamma. So I'm imagining that gamma is the jump set of U. Do you remember something similar that we did in some previous lecture? What? In the linear case, do you remember that we observed that nu must be orthogonal to characteristics? This is the analog in this nonlinear case. Okay? So let's see why this is true. I think that you can, so I have to erase something. I have to erase essentially everything. Okay. This is Ranchino-Gognot. And if you remember how we proved this, I'm wondering if I can give this to you as an exercise. Because at the end, in the linear case, this was just a line. Remember? Was the jump of our solution. And we discovered that the normal was orthogonal to the jump, essentially. Which means that this was the jump characteristic. I mean, the normal was orthogonal to capital A, no? Do you remember? It was something like nu u. In that case, there was capital A. Capital A was 1A, etc. But how we prove this, for instance, using the Gaussian theorem. So why don't we use the Gaussian theorem? So we take a domain, say a domain of this form. Say, let me call this, I don't know, B minus, B plus. So the domain is just the domain is just this red sort of box. And in this box, I want to use my divergence theorem. And this box is divided into two. So B is the union of B minus and B plus. Now, I have this box, and I take a test vector field. So I take phi C1 C in B. B is the union containing gamma. This is B. So if I take a function phi compactly supported in B, it means that the support is compact, so let me draw the support. I don't know where is the support, but what it matters for me is to allow the support to contain gamma. So the support could be this. Not very interesting, but could be also this. And this is what I want to see, because when I integrate by parts from the left and from the right, I don't see contribution here, I don't see contribution here, but I see contributions here. No? So the idea of the proof, maybe I can. So, okay, first of all, so what do we know? We know that we know that the integral over B of u phi t plus f of u phi x, this must be 0, right? But this is, so B is the union up to this line, which has 0 measure. B is the union of the open set B minus, union open set B plus. This is a Lebesgue integral, it doesn't see the line. Okay, so this is equal to the union, same object, plus the integral over B plus u phi t.
We don't care the initial condition.
No, I mean, this is, Rankine-Hugoniot is a condition interesting for positive times. Okay? Okay, I don't care about the initial condition. I could start also a time here, this curve could go here, but it doesn't matter, it's just a point. I want to see that as soon as I have a distributional solution, but this definition is very weak. But if I knew the distributional solution is piecewise smooth for some mysterious reason, I don't know, but because it is an one-log, but if I knew it is piecewise continuous, then necessarily the jump must have a normal which must satisfy this condition here. Now you see, now I am in B minus, and U is C1 in B minus. And U is C plus, and C1 in B plus. So here I can integrate by parts, separately. And what happens? Well, if I look only at here, I have a function compactly supported, so it does not, the support does not touch here, does not touch here, but generally touches here. So the boundary that I have to take into account is just this. Okay, so I have So this is the minus in minus ut plus f of u x phi. Now I use the exterior normal here. Exterior seen from B minus. Okay, so this is the integral over gamma. Okay. And I have that normal there. So I have what is this? It is nu. Maybe I should write nu minus. I don't know, nu minus. Seen from omega minus. So nu minus is this. Exterior to omega minus. Okay. Phi. So the phi is here. Scalar product. U f of u. And then I have same from the other side, minus ut plus f of u x phi. Now, however, I am looking only on the right, so I have to consider the outward normal from the other side, so I have a minus. So the same, if I use the same min minus, then I have a minus. And look that u and f of u are evaluated on gamma. And I'm assuming that coming from omega minus, I have u minus. So here, by smoothness, this is u minus, and this is u minus. On the other side, coming from omega, from B plus, I have plus here. Plus. Okay? Now I have a remark. I can use this remark. Suppose that U is a distributional solution in some open set, B minus. C1 in some open set, then it is a C1 solution there. What does it mean? It means that in B minus, this is pointwise equal to 0. Okay? Similarly, I have a distributional solution which is C1 in B plus, then it is a classical solution in B plus. Which means that pointwise, not only the integral, but pointwise, this parenthesis is 0 everywhere in B plus. So this is 0 plus 0. So we have that 0 for any phi, we have that as above, C1 C of B. We have that 0 must be equal to this minus this. Okay? Well, phi min minus scalar product u minus minus u plus f of u minus minus f of u plus. Now phi is arbitrary, and so this scalar product must be 0. Okay? Phi is arbitrary. Because I can localize, for any phi, I find something 0 for any phi localized here, and for the integral must be 0. This is the same proof that I insist to do. So it is a necessary condition, but for a piecewise smooth. As soon as we can. The problem is that L1 lock does not allow. Of course, L1 lock does not mean that there is gamma. What is U minus for L1 lock function? This is for a general L1 lock. It is not defined. This is not defined. Gamma is not defined. The jump is not defined. Everything is not defined. Okay. But as soon as it is piecewise regular, yes, it is defined. Now, why I can write this in terms of gamma? Now you see, so we have proven the Rankine-Gognon using the normal. Typically in the books you don't find this way. You find using the tangent. So look at this expression. So what I've written here, I hope that I've written something equivalent to that. So I've written that nu, one of the two normals, see, scalar product with the vector u minus minus u plus, comma, fu minus minus fu plus, this must be equal to 0 on gamma. Okay. Now, there what it is written, now which is the relation between, so a tangent vector tau tangent to gamma is what? Is, for instance, okay, I have a parameterization t here that goes into t comma gamma t, small gamma t, just a curve in the plane. Okay, so if I take the derivative, I get a tangent. So this means that tau, if I don't want to normalize it, is just 1 gamma prime. But tau is also the orthogonal to nu. So let's see what is written there, this way. Okay, I hope. So here it is written what? It is written that the scalar product between tau is 1 gamma prime. So here it is written that tau scalar product with f of u plus minus f of u minus minus u plus. No, sorry, this was down. No, sorry. Everything is down. Minus, oh, sorry, no, sorry. Okay, sorry. U minus above, upper and lower, it's the same. So now, 1 times this minus gamma prime times this, which means plus gamma prime, and I have to change sign. This is equal to 0. This is Rankine-Gognon, right? But this should be equivalent exactly to this, no? Because when tau, if I take the pair, it means that I exchange this with this and change one sign. So it should be equivalent. Okay? Please check it is equivalent. So this is usually the way you find Rankine-Gognon. Okay. So this is a necessary condition for, but not for all distributional solutions, but just for piecewise smooth. Now let's do some interesting, very interesting examples. So, example. Consider Burger's equation. Consider Burger's equation and consider the initial condition u0 of z equal 1 for negative x, 1 minus x for 0, x larger than equal than 1. Okay? So our initial condition is 1, linear, 0. This is u0. Okay, u0 unfortunately is not c1. Okay? there is a point here and a point here where the derivative is not defined actually. So u0 is not really C1. So we cannot apply directly. So u0 has these continuous derivatives at z equal, 1 minus z. So at z equals 0, z equals 1. Okay. So let's try to apply the method of characteristics. Let's try, I mean, this is not smooth, but at least we can try to apply the method of characteristics here, method of characteristics here. What do we find? U of tx is equal to u0 of z of tx. This we know. And we are in Burgers, so the relation between z and t we know also. It's x equal t u0 z of tx plus z. Okay, this is the method of characteristics. Now, you see, this gives us the characteristic lines. We know their lines are, say, x plus, x equal to t plus z if z is less than or equal than 0. No, this is another plane. Let me draw it in a... X equal t plus 1 times plus z if 0 less than z is less than 1. So in particular, for z going to 1, this is, okay, so we have, say, this, and then we have, oh, sorry. Let me draw the extremal case. So this one, these characteristics coming from 0 minus, and this coming from here, and then they are vertical. They are vertical for Z. Okay. You see that the discontinuity of the derivative here and here is the origin of this somehow. A region that will be very interesting for us in this discussion will be this corner. And we will see why. Okay, this is the plan, the picture of the characteristic lines. This is t equal 1, I think. So, and we can imagine that at least before t equal 1, we can draw the system of characteristics. We can use the system of characteristics. So, u of tx equal, let me draw it for u, 1. So it's 0 less than t less than 1. Okay, 0 less than t less than 1. 0. Here 1 minus x divided by 1 minus t. Here x less than t, comma, x greater than t, comma. This is still 4 times so what I have written there is a continuous object in the strip t less than 1 before the appearance of this point here. This is surely continuous. Unfortunately, it is not C1 because along this line here and here the derivatives jump. So this is x equal to t. And this is x equal 1. So u is continuous, and the derivative, this continuous derivative will be on x equal t and x equal 1 for 0 less than t less than 1.
For the first condition of this u,
sorry, yes, sir. For the
there will be intersection point between the two first region of xt.
Yes. This is the first time in which they intersect. What is the comment?
I mean, the second is included in the first. The second region, the value of u in the second region, 0 less than x less than t less than 1. It's
okay, yes, you're right. So I'm just taking u is equal 1 here. So here t is larger than x. Okay. Here instead t is less than x. I have to exchange. Right? Thank you. So as you can see, if I want to use the characteristics, I can go on in the definition of the solution also after t equal 1, where? Everywhere but not here. Not in this corner. In this corner I cannot go, but here I can go. So I can define u this way, even in this region, but I don't know how to define u in the green corner. You agree? So how to define u in the green corner? So how? I want to construct a distributional solution, and this is what I want to do. So this is my initial condition, it's not C1. I claim that I am able to construct a distributional solution now, by pieces, using characteristics as soon as I can, which means I can go on up to here, I can go here, 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 but I cannot, I don't know what to do in this green region. Okay? So, and we expect this, remember, still, this is a bad initial condition in the sense that it is decreasing. So this goes faster than this. So at some moment, eventually at time equal 1, there will be some discontinuity. Ux, the derivative in x should blow up. Or maybe here it is piecewise constant actually, in any case. So, so now, its time is over. So I would like you to try, well, maybe, to try to reasonably define this the U in the green region using I give you the idea of how to go on. So here U is constantly equal to 1. Do you agree? Because characteristic, I go back and I'm finishing where U0 is 1. Here the same, in this region, U is equal to 0. But here no, is linear, say, not 1 or 0. So, I have the problem of the green corner, no? I have the problem to define U in this green corner. And from the left, U is 1. And from the right, U is 0. What could we do? One possibility could be that we select some gamma here. Gamma. Gamma, you remember, gamma was a piece of curve starting from A to time B. B could be plus infinity, yeah? So the idea is to, maybe we are able to select some gamma, no, which is graph with respect to this axis, so some actually half line. And we could define U1 here, 0 here also, provided that gamma satisfies the Rankine-Hugoniot. Because this, we cannot choose any gamma if we want a distributional solution. And this distributional solution will be piecewise smooth. So necessarily it must satisfy the Rankine-Hugoniot. So we cannot select any gamma. There is only one gamma here, in which we could reasonably try to put U equal 1 here, 0 here, Rankine-Hugoniot, which gives me my line, the slope of my line, and hope that this is distributional solution. So this is the idea. Let's see if you are able. You find this type of constructions in any book, I think. For instance, in the book of Evans or others books on conservation laws, you find this kind of things.